So far, this topic has given you a general overview of the equipment in your plant. In this unit, we'll review some of the concepts that you've learned by applying them to a common operator activity, a load change. From there, we'll focus our attention on an important component found on all moving equipment, bearings. You'll learn about the various types of bearings and the ways in which they are lubricated. Then we'll discuss pollution control. Pollution can be caused by the incorrect operation of a power plant, so it's necessary for you to know what pollution is and how it can be controlled. And finally, we're going to talk about safety. We'll give you some valuable advice on how to keep from getting hurt on the job. The power industry enjoys a remarkable record for safety, but no matter where you work, if you get careless, there's a good chance that you'll get hurt. Well, enough of calming attractions. Let's get started on our discussion of load changes. Now, we've already stressed that load must equal demand. Whenever the demand for power increases or decreases, the power generated in your plant must change accordingly. Changing the supply of power to meet demand is called a load change. Load changes are a routine part of an operator's job. While on the job, you need to be aware of what is happening to your unit at all times. To do this, you pay close attention to all of the indicators in the control room. You'll need to do the same thing during a load change, but you'll also need to pay particular attention to 4 important flow rates: steam flow, feed water flow, fuel flow, and combustion air flow. In most systems, the dispatcher calls the control room and requests the operator to make a load change. In this case, the operator makes the load change by operating the turbine governor. This causes the opening of the control valves to increase or decrease depending on which way the controller is moved. Now, keep in mind that there isn't a single controller that does everything. There are usually separate control systems for the turbine, feed water, fuel, and combustion air. Of course, control systems vary from plant to plant, and you'll need to learn exactly how yours is arranged. But what generally happens is that the operator changes load on the turbine, and the rest of the systems automatically adjust accordingly. The operator must change the load slowly in order not to exceed the recommendations made by the manufacturer. It's not unusual for the load change rate to be 4 or 5 megawatts per minute. This means it would take 20 minutes or more to complete a 100 megawatt change. Now, so that you can actually see what happens during a load change, let's take a look at a typical example. We'll use specific numbers during this example to make the load change easier to follow. You should not attempt to memorize these numbers since they'll vary from unit to unit. Instead, look for what the operator is doing during the load change and how his actions affect the unit. Keep in mind that while we don't want you to memorize these numbers, the specific flow rates for your unit are very important. We'll be using a unit rated at 200 megawatts for our example. Now let's say that at the start of the shift, demand is relatively low and the unit is only required to produce 100 megawatts. But it's capable of producing an additional 100 megawatts if necessary. In order to produce 100 megawatts, the steam flow through the unit is around 680,000 pounds per hour. Since feed water flow and steam flow must be balanced, the feed water flow is also 680,000 pounds per hour. The fuel requirement for this unit producing 100 megawatts is around 37 tons of coal per hour. To burn 37 tons of coal per hour, the operator has to mix it with about 1.5 million pounds of combustion air per hour. Typically, when the demand for power increases, the operator will get a call from the dispatcher to increase the load a certain amount. The change for this example requires the operator to increase the output from 100 megawatts to 200 megawatts. In other words, the output of the unit must be doubled. The operator begins the load change by going to the turbine governor and opening the control valves. He does this slowly, while watching the steam flow indicator so he won't exceed the manufacturer's specifications. In order to produce 200 megawatts of power, the steam flow needs to double to 1,360,000 pounds per hour. As the steam flow increases, it causes a change in steam pressure. The control systems for the unit sense the changes in a steam flow or steam pressure and adjust their systems accordingly. The feedwater control system responds by adjusting feedwater flow so that it matches the increase in steam flow. In this way, the steam and feedwater flow stay pretty close during the increase in load. The automatic control systems for fuel and air sense the decrease in steam pressure and begin adjusting the fuel flow and combustion air flow to restore steam pressure to its desired level. By the time the unit is producing 200 megawatts, the fuel flow will have doubled to 74 tons per hour, while the combustion air flow will have doubled to 3 million pounds per hour. Now, while all of this is going on, the operator is making routine checks of the flow rates and comparing them to what he has seen under the same conditions before. Should he spot what he considers a potential problem, for example, the combustion air flow rate may be too low, he may have to make adjustments to an automatic control system. Now, in most cases, this will restore the unit to normal operating conditions. However, if it doesn't, the operator will have to take manual control of the faulty system. Taking manual control of any system requires you to be responsible for manually adjusting the functions of the system, which normally are adjusted automatically. In situations like this, the operator must apply everything that he has learned about the steam cycle and the unit he's operating. Well, we've covered a great deal in this segment. We've seen that steam flow, feedwater flow, fuel flow, and combustion air flow must be carefully monitored during a load change. It's the operator's job to monitor pressure, flow rates, and other indicators to make sure that the load change is proceeding properly, and to make adjustments if the automatic systems fail to respond correctly. Now would be a good time to stop the tape and read the material in the text. If you have any questions, ask your instructor for help. Operators are responsible for a lot of equipment in the plant. While there are many differences between these pieces of equipment, one thing that they all have in common is bearings. Bearings are vital to the operation of almost all equipment. Without them, equipment can't run. As an operator, you must know what bearings are and how they work so that you can keep your unit running smoothly. Bearings are used to overcome friction. Friction is the resistance to motion that exists between two bodies in contact with each other. In order to move one or both of these bodies, friction must be reduced. The majority of bearings fit into one of two categories: sliding surface bearings and rolling contact bearings. With sliding surface bearings, two surfaces with a lubricant between them slide over each other like so. With rolling contact bearings, one surface rolls over another surface with lubricant in between. Now, regardless of the bearing type, all bearings perform three functions. First, they carry loads. Second, they reduce friction. And finally, they position a moving part. The terms bearing and bearing surface are used in many different ways. In this tape, the term bearing refers to a device that carries loads, reduces friction, and positions a moving part. On the other hand, the term bearing surface refers to the specific parts of the bearing that come in contact with a moving shaft or similar moving part. Okay, so far we've said that bearings are devices that carry loads. A good example of this is the shaft of a pump. The shaft and rotor of a pump are actually supported by bearings. It's the bearings that enable the shaft to rotate. We also said that bearings are used to reduce friction between moving parts of equipment. Most bearings contain grease or oil, which is used as a lubricant to reduce friction between the moving surfaces. And finally, we said that bearings are used to position moving parts. Bearings keep parts in their proper place and reduce the chances of undesirable movement. For example, a shaft must be able to rotate in order to perform its job. However, the equipment attached to this shaft could be seriously damaged if the shaft were allowed to move end to end. The shaft could also be damaged if it were allowed to move away from the center line. End-to-end movement is called axial movement because it's movement that follows the axis of a shaft. Movement that moves away or radiates from the center line is called radial movement. A bearing may be designed to prevent either radial or axial movement, or both. Now, let's look at some of these designs. First, we'll talk about sliding surface bearings, and then we'll look at rolling contact bearings. As we do, keep in mind that there are many variations in bearing design, and we're only going to look at a few of these. Now, bearings are often named for the type of movement that they're designed to prevent. This sliding surface bearing is sometimes called a radial bearing because it's designed to prevent radial movement. The bearing has two parts, a housing and the bearing surface. I'll remove part of the housing so that you can see the bearing surface. When it's completely assembled, the housing holds the bearing surface in place. The bearing prevents radial movement of the shaft. But as you can see, axial movement is still possible. Axial movement can also be prevented by a sliding surface bearing. In this case, a thrust bearing is used. This bearing can also be called an axial bearing because it's designed to prevent axial movement of the shaft. Here's a shaft. Attached to the shaft is a raised section called a collar. If the shaft moves, so will the collar. Around each side of the collar are bearing surfaces. They fit around the shaft without touching it and are slid up until they contact the shaft collar. They're held in place by a housing. The housing can't move because it's usually bolted in place. The housing also contains grease or oil that lubricates the bearing surfaces. Seals located where the shaft penetrates the housing keep lubricant from leaking out of the housing. Whenever the shaft tries to move axially, the collar pushes against the bearing surfaces and movement is stopped. Actual contact of the collar with the bearing surface is prevented by a thin layer of lubricant. Well, so far we've been looking at sliding surface bearings, but rolling contact bearings can also be used to prevent radial and axial movement. Let's look at the parts of a common rolling contact bearing. First, there's an inner ring. Then there's rolling elements that are held in place by a retainer, an outer ring, and a housing. The outer ring is attached to the housing. As in most bearings, the housing is attached to a stationary structure. In this bearing, the inner ring is attached to a shaft. The inner ring and the shaft rotate together while the outer ring remains stationary. The arrangement of the rolling elements between two rings maintains equal distance between the rings and prevents radial movement. Now, here's a cross-section of another type of rolling contact bearing called a tapered rolling bearing. It can handle both radial and axial movement. This ring is stationary, and this one moves with the shaft. The tapered rollers keep an equal distance between the two rings and prevent radial movement, just like the rolling contact bearing we saw earlier. The tapered rollers also prevent axial movement. If the shaft tries to move this way, the rollers meet the outer ring and the shaft is unable to move. Now remember, lubricant in the bearing prevents actual contact of the parts. This bearing will prevent axial movement in this direction only. But the addition of a second bearing will prevent axial movement in both directions. A rolling contact thrust bearing, which prevents axial movement only, is designed differently. In this case, the shaft, like we see here, has a ring attached to it. The shaft and ring turn together. Rolling elements fit over the shaft and meet the rotating ring. A stationary ring also fits over the shaft and is placed up against the rolling elements. The stationary ring is attached to a housing. Lubricant keeps the parts from actually touching each other. Now keep this in mind as we describe how the bearing works. When the shaft tries to move, the rotating ring pushes against the rolling elements, and the rolling elements push against the stationary ring. Since the stationary ring is attached to the housing, axial movement is prevented. This type of bearing prevents axial movement in this direction only. We've now seen how rolling contact bearings and sliding surface bearings perform two of their three basic functions: supporting loads and preventing undesirable movement. Now, all along, we've indicated that bearing parts don't actually touch. The parts are separated by a thin film of lubricant. Well, that's what we're going to look at next. We'll see how bearings reduce friction. We'll use a typical sliding surface bearing. Friction is reduced in this bearing by a process known as film lubrication. With this process, a thin layer or film of lubricant is distributed and maintained between the bearing and the shaft during rotation. The space between the bearing and the shaft is filled with oil. When the shaft is at rest, most of the oil is squeezed out between the bearing and the shaft by the weight of the shaft. When this happens, the bearing and shaft are in metal-to-metal contact. As the shaft begins to rotate, its motion drags oil underneath it. Oil sticks to the shaft and is carried between the two surfaces. The shaft is lifted away from the bearing by the oil film and is now supported on the film of oil. As the rotational speed increases, more and more oil is drawn under the shaft. The oil forms a wedge that keeps the surfaces of the shaft and bearing apart. If the oil wedge were not present, the shaft and bearing could come directly in contact with each other, and the operating temperature of the bearing would increase due to friction. This could seriously damage the bearing by greatly increasing wear. Rolling contact bearings also use an oil film for lubricating the bearing. Oil or grease within the bearing housing is distributed between the bearing parts as they rotate. Now, even when a bearing is properly lubricated, a certain amount of friction still remains and produces heat. As an operator, it'll be your job to periodically check bearing temperature. Too high a temperature, it's a sign that the bearing may not be functioning properly. There is a distinction that must be made when talking about bearing temperature. First, there's the temperature of the bearing housing, and second, there is the temperature of the bearing itself. This is significant because the two temperatures can be considerably different. You'll need to know which of these you're checking. There are a variety of ways to check the temperature of a bearing. The easiest method is to read the temperature directly from a temperature indicator on the bearing. However, most bearings don't have temperature indicators, and it's necessary to use another method. A common approach is to feel the bearing housing with your hand. This may sound somewhat crude and unscientific. However, with experience, you'll be able to tell quite accurately if a bearing is running too hot. Remember, however, that this test is only for the housing temperature and not the actual temperature of the bearing. There are also instruments for determining temperature. This operator is using a pyrometer to measure the temperature of a bearing housing. The probe is placed on the bearing housing and held there for a period of time to allow the probe to warm up. Then, the temperature can be read directly from the pyrometer. One thing to remember when taking temperature readings is that they will not be accurate until the equipment is operated a certain amount of time. This time is different for each piece of equipment and is called startup time. You must be certain to allow a bearing enough time to reach its operating temperature before you take your readings. Temperature isn't the only thing that an operator must check on a bearing. You also need to check for vibrations and listen for unusual sounds. Unusual sounds and excessive vibration can be an indication that the bearing is not functioning properly. An instrument used to check vibration is called a vibrometer. Its probe is placed on the bearing housing, and the amount of vibration is read directly from the meter. Your plant may have a record for the vibration readings on major pieces of equipment. If so, you can compare these readings. If the readings taken are outside the normal operating trends for the piece of equipment, you should suspect a problem. On large equipment, like this turbine, vibration instruments may be permanently installed. This allows the operator to take readings directly from a recorder or meter. We've now seen how bearings are used to support loads, reduce friction, and position moving parts. We've also seen how an oil wedge is used to lubricate bearings, and we've seen the specific checks that an operator may perform for temperature and vibration. In the next segment, we'll continue our discussion on bearings and look at systems used to lubricate them. But for now, read the material in your text and answer the questions. If you have any questions, ask your instructor to help clear them up. In segment 2, you learned that moving equipment depends on bearings to reduce friction. This segment will look at how bearings are lubricated and various lubrication systems that you may find in your plant. As an operator, it may be your job to maintain the lubricant levels on a variety of machinery in the power plant. To do this job properly, you must be familiar with lubricants and lubrication systems. You'll need to know which lubricant is right for which machine, and how much lubricant needs to be added for efficient operation. In order to help you do your job properly, plants have a lubrication identification system. Using the wrong lubricant may seriously damage machinery, so it's a good idea to check the manufacturer's recommendations or plant procedures before adding lubricants to any system. If you're ever in doubt, ask your supervisor if the lubricant you have chosen is right for the machine you're servicing. Now, in this segment, we'll cover the two most common types of lubricants, grease and oil. We'll cover grease lubrication first, then go on to look at several oil lubrication systems. Okay, let's get started. Grease is a common type of lubricant that has many uses in the power plant. There are several methods for getting grease into a bearing. We'll cover two of them: greasing with a grease gun and greasing with a grease cup. Grease is usually applied to a bearing by using a grease gun. Grease is injected into the bearing through a grease fitting on the bearing housing. A grease fitting is a small rounded projection from the housing that has a hole through it. The fitting on the grease gun must match the fitting on the housing. To grease a bearing which has a fitting, it is often necessary to remove a drain plug from the housing before any grease is added. The plug is removed so that old grease or excess grease can drain out. Wipe off the grease fitting and make sure the opening is clear. Then, attach the gun to the fitting on the housing. Applying grease while the bearing is in motion helps to distribute the grease more evenly. Grease should be added slowly until it begins to come out of the drain. The machine should be run for several minutes afterwards to make certain that all excess grease has been forced out of the drain. Then, wipe off any excess grease and replace the plug. If there isn't a drain plug, you must be careful not to add too much grease. Too much grease can cause overheating and damage to the bearing. How much grease you do add will depend on your plant's maintenance schedule. Another method of greasing a bearing is to use a grease cup. A grease cup is a container with grease in it that is mounted right on the housing. To force grease into the bearing, you turn the top of the cup. Usually, 1 to 2 turns is sufficient to grease the bearings. Again, your plant may have specific guidelines concerning how much and how often a grease cup should be operated, ask your supervisor about them before you start. Also, make sure there is enough grease in the cup before you begin. If it's nearly empty, refill it with the right type of grease. Well, now that we've seen how greasing is accomplished, let's look at oil lubrication and various systems that can be used. We'll first discuss how oil is removed from original containers and then go on to look at specific oil lubrication systems. Oil is shipped to most plants in large barrels or drums. These original containers are usually too large to carry around the plant, and so the oil must be taken out of them and carried in other containers. There are two basic methods for removing oil from a barrel. The first is by using a barrel pump, and the second is by using a spigot. When installing a barrel pump, the first step is to clean any dirt or debris from the top of the barrel. By doing this, you reduce the possibility of contaminating the oil in the container. Once the top of the barrel is clean, the barrel is opened. For the pump to operate properly, the barrel usually needs to be vented. This is done by removing the small vent cap on the top of the barrel, as you see here. Another job that must be done is cleaning the barrel pump. These pumps can sit around for a while and dirt may collect on them. Once cleaned, the pump is inserted through the open hole in the barrel and screwed into place. To operate the pump, simply rotate the handle. Whenever pumping is complete, the vent cap should be reinstalled to keep the oil clean. The pump is almost always left inside the oil drum until the drum has been emptied. A second method of removing oil from a barrel is the use of a spigot. The spigot is installed in the same opening as the one used for the pump. Therefore, the same preparations are necessary to keep the oil clean. Once the top of the barrel is cleaned, then the spigot can be screwed into the opening. Make sure it's firmly in place. The barrel is then turned on its side. If the barrel is full of oil, like you see here, it can weigh over 400 pounds. You have to exercise caution to prevent it from getting away from you. Next, you need to open the vent so air can enter the drum as oil leaves. After the vent is opened, lifting a spigot will allow the oil to flow. After oil has been drawn into the container that you're going to use, be sure to replace the vent cap. Otherwise, dirt could get into the barrel. Now, once you've removed oil from a barrel, never return it to its original container. If you do, you greatly increase the possibilities of contamination. Contaminated oil can cause serious problems because dirt and other particles could get into a bearing and scratch or otherwise damage its components. All contaminated lubricants should be clearly labeled and properly discarded or recycled. Now that you know how to remove oil from its original container, let's look at some lubrication systems for bearings. We'll show you how to put lubricant into the bearing. The first system that we'll discuss is the oil ring lubrication system that is frequently used on sliding surface bearings. Now, as you know, sliding surface bearings consist of a bearing housing which surround a shaft. Now, in many cases, the housing and bearing surface are divided into an upper and lower half, like this one, for ease of maintenance. In an oil ring lubrication system, the lower half of the housing contains an oil reservoir, and an oil ring is placed around the shaft. The lubrication process is really quite simple. Half of the ring is always suspended in the oil reservoir. So, when the ring and shaft turn, oil sticks to the ring and is deposited onto the shaft during rotation. The oil then spreads throughout the bearing and proper lubrication is achieved, as you can see here. A continuous film of oil is supplied to the bearing and shaft by this method. Now, periodically, the oil reservoir must be checked. This is usually done by reading the level of oil on a sight glass. The normal indication would show oil halfway up the inside of the glass. If a sight glass is not present, the bearing might have a dipstick similar to the one in most cars. That will indicate the oil level in the reservoir. To fill the reservoir, oil is poured directly into it until either the sight glass or dipstick indicates a normal level. On some bearings, there may not be a sight glass or a dipstick. In this case, there is usually a spill hole located on the housing where the normal level of oil should be. The operator can remove the spill hole plug and look inside the reservoir to check the level. If oil is needed, the operator removes the fill hole plug from the top of the bearing and pours oil into the hole until oil reaches the spill hole. An oil level at the spill hole tells the operator that the reservoir is full. Next, he should replace the spill hole and the fill hole plugs. The next system for oil lubrication that we'll look at is called a constant level oiler. As its name implies, this type of system maintains a constant level of lubricant for a bearing. As you can see here, a constant level oiler has an oil cup that is connected to the housing by a tube. The oil level in the cup is the same as the oil level in the housing because of the tube that connects them. A reservoir that has an opening in its bottom is placed in the oil cup. As long as the reservoir has oil in it, the system will automatically maintain the proper level of oil in the bearing housing. Here's how it works. As the level of oil in the housing drops, oil begins to flow through the tube into the housing. This causes the level in the oil cup to drop. The oil continues to flow until the levels in the cup and the housing are the same. When the level in the oil cup falls below the opening in the bottom of the reservoir, oil flows from the reservoir into the oil cup. The flow stops as soon as the level in the oil cup is up to the bottom of the reservoir. When this happens, the oil in the housing is back to its proper level. The reservoir in this type of oiler is transparent, so its level can be checked. It's refilled by lifting it off the tube, turning it upside down, and pouring oil into it. It's important that you periodically check the level of oil in the housing. If for some reason the tube should become clogged, the oil reservoir will remain full. However, no oil will be supplied to the bearing, and this can result in damage to the bearing and unnecessary repairs. The forced lubrication system is another type of system that we should discuss. A forced lubrication system continually circulates a steady supply of oil through one or more bearings. In this type of system, there is a pump that pushes oil into the bearings, and it's usually collected in a reservoir so that it can be pumped through again. Oil filters and coolers are often used in a forced lubrication system. Filters keep the oil clean by using a filtering medium, such as bags or screens. Coolers remove heat that the oil picks up from the bearings. So, a forced lubrication system actually accomplishes three things. It lubricates the bearings, it keeps the oil clean, and it keeps it cool. There's usually a sight glass on the oil reservoir. If the oil level gets too low, oil has to be added. Well, the last type of lubricator that we'll look at is the drip feed type. Drip feed lubricators are systems that allow oil to slowly drip into a bearing. In this type of oiler, there's a transparent reservoir that is set above the bearing. A small hole in the bottom of the reservoir allows the oil to drip through. This keeps the bearing steadily supplied with fresh oil. A knob on the top of the reservoir is used to adjust the rate of the drip. The proper rate can be determined by either referring to the operator's manual or by asking your supervisor. There's also a lever that is used to stop the flow of oil when maintenance is required or when the machine is shut down. Generally, new oil is added by pouring it into the top of the reservoir until the reservoir is full. Any or all of these systems may be used in your plant. you might ask your instructor to point them out to you the next time that you're in the plant. Regardless of the system used, it's important to keep in mind that the system will not perform properly if the wrong lubricant is used. And to avoid this, make certain that you follow your plant's procedures for lubrication and that you make all of the necessary checks that are called for on the periodic maintenance schedule. Well, we'll stop here so that you can read the material in the text and answer the questions at the end of this segment. If you have any questions about lubrication, make certain to clear them up with your instructor before going on to the next segment. Electrical power is truly amazing. With it, we can turn night into day, keep roads and highways safe, or run the thousands of machines that might make our lives a bit more convenient. However, everything about electricity isn't perfect. Certain byproducts of power production can be harmful to our environment. I'm speaking about pollution. The power industry is one of the least polluting industries in the nation, but it's no different from other industries in its potential for causing polluting agents to be released into the environment. Long ago, the power industry realized its responsibilities in this area and has spent vast quantities of time and money on environmental research and pollution control. Many of the processes which limit the amount of harmful substances that reach our environment require special equipment, and that's where you come in. You'll be operating this equipment. If you don't understand what the equipment does or how it's supposed to operate, you could be causing pollution. Now, in this segment, we'll present a general overview of the four most common sources of pollution in a power plant, the types of polluting agents that they create, and the steps which are typically taken to minimize pollution from each of these sources. By understanding where pollution comes from, you'll be better prepared to properly operate anti-pollution equipment. One of the largest potential sources of pollution to the atmosphere is the power plant's boiler. Small particles called particulates are released from the boiler and discharged through a stack. Particulates can travel great distances before settling to the ground, and the mess they cause can be a real nuisance. However, a greater harm comes from breathing in particulates because they can cause respiratory problems. Particulates are more of a problem in coal-burning plants than other power plants. For this reason, most coal plants are equipped with devices called precipitators, which separate particulates from the flue gas before it goes to the stack. Precipitators may be before the air preheater, or as we see here, after the preheater. When precipitators are working properly, very few particulates are released into the air. In addition to particulates, boilers also produce gaseous pollutants. Fossil fuels contain various amounts of nitrogen and sulfur, which combine with oxygen during the burning process, producing nitrogen and sulfur oxides. These pollutants are not easily seen. Therefore, they're detected by monitoring devices which analyze air quality. Unfortunately, we don't as yet know everything about the effects of oxides on the environment. One thing that we do know, the long-term effects of oxides in the air are harmful to plant and animal life. And for this reason, the amount of nitrogen and sulfur oxides and all other pollutants discharged into the atmosphere is limited by law, and it's therefore necessary to control them. One method of controlling sulfur oxides is through the use of scrubbers. Scrubbers are located in the path of flue gas just before it enters the stacks. Scrubbers use chemical processes to reduce the amount of sulfur oxides in the flue gases. Another method that is used to control sulfur oxides is the burning of low sulfur fuel. Nitrogen oxides present a different problem. Scrubbers and other external anti-pollution equipment do very little to reduce the amount of nitrogen oxide released by a boiler. Instead, we control their formation by controlling furnace temperature. A number of methods are employed to reduce the temperature of furnaces. Adjusting the fuel-air ratio will slow down combustion, and recirculating flue gas back through the furnace will accomplish the same thing. You'll need to find out what methods are used in your plant to reduce the amount of nitrogen oxides released into the atmosphere. Another major source of potential pollution is the condenser. The major job of the condenser is to remove heat from steam. So what we're concerned with is thermal pollution. Depending on the type of water cooling system, heat is released directly from the plant into lakes, oceans, rivers, or into the air through cooling towers. Heat released into a lake, ocean, or river can raise the water temperature. If the temperature gets high enough, it can affect animal or plant life in the area. Now, the amount of heat that can be released into a body of water is restricted. At times, you may adjust load on your plant to control the amount of heat released in this way. Part of your job as an operator is to monitor the condenser outlet temperature and to maintain it within the limits prescribed by your plant's operating procedures. Heat that is released into the atmosphere by cooling towers creates different problems. The water vapor created by the heat in the cooling towers may cause fog and low visibility under certain atmospheric conditions. Water vapor that condenses in freezing weather may cause hazardous icing conditions. If these conditions become severe enough, the operating level of the plant may need to be reduced. The third source of pollution that we need to cover is wastewater. This comes from various plant equipment and especially from the boiler in the form of blowdown. Blowdown is necessary to plant operation in order to get rid of silt and other impurities. But along with silt, blowdown often contains chemicals. If these chemicals are discharged without being treated, they might harm the environment. You need to make certain that wastewater is properly treated before it's discharged. Each plant has its own wastewater treatment system, and you'll have to know how to operate yours. The final type of pollution is difficult to eliminate completely. However, its effect is primarily limited to the plant. We're talking about noise. Machinery creates noise, and noise pollution can, in the long run, cause premature hearing loss or partial impairment. Excessively noisy areas are marked with signs like this. Ear protection is your major safeguard against this type of pollution. Your plant most likely has specific procedures on ear protection, and you should be familiar with them. In other units, we'll give you more specific information about pollution safeguards and your role in minimizing pollution. For now, remember that the boiler, condenser, plant wastewater, and noise are the major sources of pollution, and that left unchecked, serious problems can result. Now, stop the tape and read the material in your text, and then answer the appropriate questions. This is a scene that no one really enjoys seeing. Unfortunately, it's a scene that's repeated at factories and plants across the country roughly 1,400 times each year. The fact that the power industry enjoys an excellent record for safety on the job is of little consequence if an accident happens to you. The truth of the matter is that the majority of accidents usually do not just happen by themselves. In many cases, the worker causes the accident to happen by not following the planned safety procedures or not using plain old common sense. Now, in this segment, we're going to show you how common sense and safety go hand in hand. We'll be looking at you and how important you are to yourself and to those around you in preventing accidents from occurring. We'll also show you that you not only need common sense, but you'll also need specific safety procedures that cover the jobs you'll perform. Signs in the plant make it easy to see that power plants have the potential for accidents. However, by strictly enforcing safety procedures and requiring operators and other personnel to use protective equipment, power plants have become one of the safest places in the world to work. But regardless of the number of rules and procedures that govern safety, some accidents occur, usually when a worker forgets to use common sense. For example, take a look at that guy working up there. He's followed all the proper safety procedures. He's posted barricades around the work area, secured his tools to his belt. Even so, there's always a possibility that something could be dropped. A hammer, a wrench, a bolt, it doesn't really matter. If it hits you from that height, it's going to hurt. For this very reason, plants have strict policies about wearing head protection. This sign means that you don't enter the area without a hard hat. But make sure that your hard hat is one that is approved for power plants. It should be made of plastic or other non-conducting material. Never metal. Your job is power production, not acting as a conductor for current flow. Of course, your head is not the only part of your body that needs protection. You depend on your hands, feet, eyes, ears, arms, and legs to do your job. So make sure that equipment you use matches the job that you need to do. Of course, common sense is up to you. Procedures will tell you the precautions that you must take when performing specific jobs. For example, when doing any job where particles can get into your eyes, you should wear safety glasses or goggles. Common sense says so, and your plant procedures may also say so. But here, eye protection alone isn't enough. You need the added protection of a face mask to keep dust, ash, and dirt from choking you. And even goggles and a face mask aren't enough when working around chemicals. Sometimes you'll need a rubber suit with a hood and gloves to guard against spills or splashes. Your plant safety manual will outline the requirements for these and other jobs. A power plant is full of machinery that generates heat and steam and makes noise. To protect yourself from hearing loss, it's a good idea to wear approved ear protection in noisy areas. To protect yourself from heat and steam, you can wear a long-sleeve shirt and cotton gloves. Burned shirts and gloves are easily replaced. Burned tissue and skin takes a lot longer. Remember, you won't feel superheated steam or hot water until it's too late. So protect yourself. It makes good sense. And while you're at it, take care of your feet. Canvas tennis shoes and sandals may be very comfortable, but they offer very little protection from hot pipes or heavy objects. In fact, because hot water will soak into canvas shoes and be held against your skin, they can contribute to an injury. Your plant's procedures will have specific requirements for proper footwear. Make sure that you understand them and follow them. Now, while using protective equipment will reduce the severity of accidents, your goal should be to avoid accidents. You have to extend your common sense to make safe working procedures a habit. It only takes a fraction of a second for long hair, shirt tails, rags hanging from pockets, unbuttoned shirt sleeves, or loose or torn clothing to get caught in moving or rotating equipment pulling you into the works. You should also be careful with watches, rings, neck chains, or other items of jewelry. While they're attractive, they're also conductors. A watch or ring that comes in contact with a hot pipe or electrical source can have serious consequences. The best advice is to leave them in your locker or at home. Another good way to avoid accidents is to keep your work area clean. It's impossible to prevent all leaks and spills, but it is possible to keep them from becoming a safety hazard. If you find oil, water, or any other substances on the floor, it's a good idea to take the time to clean it up. A few minutes with a rag or mop could prevent a few weeks in the hospital. Well, so far, we've stressed the importance of taking care of yourself on the job. But a large part of your responsibility will be to assure the safety of others. As an operator, you'll probably never have to clean or repair a furnace or boiler. But you will be responsible for isolating all types of plant equipment so that someone else can work on it. The way this is usually done is called tagging or tagging out. Every plant has specific tagging procedures that must be followed to ensure the safety of maintenance crews. Basically, when a system is tagged out, the operator places a color-coded tag on the components that isolate the equipment which is to be worked on. That is, tags are put on all components that could create a hazard if they were operated while the maintenance crew is at work. A piece of equipment that is tagged for personal protection should never be operated until the tag has been removed according to plant procedures. What safety really boils down to is remaining alert to anything that could cause harm to yourself or others. If you ever have a question as to the proper procedure to follow, consult your plant's safety manual or ask your supervisor. Well, we've covered a lot in this topic on basic power plant operation. We reviewed some basic information concerning power production, boilers, and turbines. And then in this unit, we applied this knowledge to the specific operator task of a load change. And we saw some of the operator's responsibilities during a load change. Next, we looked at bearings. We saw how this relatively small component makes it possible to support loads, reduce friction, and position moving equipment. We also saw how bearings are lubricated using grease or oil, and we stressed the importance of using the right lubricant for each bearing. Then we talked about a potentially undesirable byproduct of power production, pollution. We showed you how pollution is being controlled and indicated the importance of making sure that the anti-pollution equipment in your plant is doing its job. Finally, we looked at some basic procedures and safeguards to help you protect yourself on the job. We pointed out that both common sense and your plant's safety procedures play a role in your on-the-job safety. The point we've tried to make in the last 4 tapes is that your job as an operator involves much more than simply learning what all the dials, switches, and indicators for a unit mean. In your position, you must take into consideration your effect on the environment, on your fellow workers, and on yourself in order to really be able to do all the things your job requires. Well, we'll stop here so that you can read the material in the text and ask your instructor to clarify any points that you don't understand.